introduction. I am Yaroslav Dubik from Kyiv, Ukraine, and today two of my talks are related to geometrical defects in gas pipelines, namely dents and metered bends. Metered bends mean dents means of defects of small angular of misalignment between weldings. So first one is about dent. Here is the concise content of my report. First one I will talk about mathematical background, then about harmonic dent, single dent, and some examples for practice. Here are the sketch of forces and stress resultants. And here are all these equations, shell equations based on Donald-Mushtari thin shell theory. All these equilibrium equations, physical equations, geometrical equations, they lead to this equation of 8th order. And generally it's complicated to solve, but in this case we will find a complete solution for these equations. I will talk about it a bit later. About how we'll account for that. So Kaledin in 1972 proposed an approximative equivalent loads method. Kaledin had a very simple idea that our imperfect shell under pressure can be composed from two cases: a perfect shell under our system of loads and perfect shell under equivalent loads. The point is that our imperfections mean in change of curvatures, so additional loads will appear on these curvatures. Another issue is how our form of dent will be. Generally, this equations is used by many researchers, but these equations is better than this because we use the exponential functions and it can be easily extended for a 3D dent. Here we have dent dimensions like dimension in axial direction and dimension in circumferential direction. Here are this visualization of these dents, and now we came to harmonic dent. Harmonic dent means that we have an wave shell, an infinite dents in axial direction and obviously limited dents in circumferential direction because we are limited to circle length. But these simplifications allow us to obtain an accurate solution, and this solution will be used later for single dent, and also it's useful by itself because we can test the Kaledin approximate load method, and also if we have dents which rely from a big distance from each other, we can also use this solution. And so using this expansion, this form of dents, we can guess our three main displacements: axial, circumferential, and radial displacements by these expansions, and we will get the solution of our systems. We'll have a system of three linear algebraic equations with respect to three of our constants. And here is our loads. And these loads can be easily extended to account for additional curvature from shell deformation. So this system can be easily solved, and we will get a solution for our harmonic dent, where here we have m and n constants. They mean the waves in axial and circumferential directions. We can extend our solution using the Fourier series expansions to a single dent. Just we have to expand our forces, and thus we will obtain our stress resultants as usually our stresses, membrane and bending stresses. We have compared our solution with numerical results made in shell in ANSYS. And so here is a comparison. Solid line is the analytical solution, and dashed lines are the numerical solutions. As we can see, we can quite well describe the form of our curve. Of course, we have some discrepancies in the ultimate value of stress concentration, but this solution can be used for parametric study. The point is that many researchers haven't investigated the form of the dent. It means when we have a disproportional dent in axial direction or in circumferential direction, these cases are omitted. And as we can see, this is quite important. At the first glance, we can see that for pressure loading, we have more coefficients of concentrations, and these coefficients of concentrations are larger for these disproportional dents, as for pressure and as for axial loadings. Here is one example from practice. There was an accident on a gas pipeline. It was a burst there. So the first idea was that we had a material degradation. We have cut off some specimens from this pipeline. We have tested them, but there was no significant material degradation. So our idea was that this burst was caused by geometrical imperfection, namely by dents. So here you can see one of these dents, and we have calculated the stress concentration for this dent. And as you can see, we have a large stress concentration compared to the nominal stress level. Here is the stresses for this whole pipe, membrane stresses and bending stresses in axial and circumferential direction. And here is the conclusions of this work. Mainly that we have developed quite a simple way to analyze these dents as harmonic dents, and this can be extended as this in a semi-analytical manner using the Fourier expansion for a single dent. And of course, we can calculate this concentration due to pressure on axial loading. And that's, this loading, we can, with this analysis, we can analyze how this the dent form how this dent form affects our pipe strength. Thank you.